to lecture 28. So, in lecture 27, we introduce the simplex search method for multivariable functions. In this lecture, we will talk about Nelder-made simplex search method, which is an improved version and one of the most widely used search technique for multivariable functions. So, in case of simplex search that we discussed in our previous lecture, we have seen that when the optimization is approached, the simplex can start cycling. In that case, you can take the midpoint of the sides of the simplex and can reduce the size of the simplex and again proceed. In case of Nelder-made simplex method, what we do is we consider that it is not necessary that the structure or the geometry will always be regular. It is possible to make use of a flexible simplex. That means we can expand or we can contract the simplex. Let us consider this. You have a two-dimensional simplex. That means you are solving a two-dimensional optimization problem. So, you have a two-dimensional simplex, basically an equilateral triangle. So, you have three vertices. So, you have one vertex, let us say vertex number 1, which is worst. So, you would like to reflect it. Now, you see the reflected point that you get is the best among all other points. That means that is the direction in which its function value is decreasing and it is decreasing well. So, definitely you would like to go in this direction further. So, in that case we not only reflect it, but we also expand the simplex in that direction. Similarly, if the reflected point obtained by the same technique that we have discussed in our previous lecture gives you a point which is worse than the previous worst point, then we definitely would like to come back. So, we contract along the same direction through the centroid and form a simplex, but we do not go to the point after reflection, we contract it. So, in case of Nelder simplex search method, based on the function values, we will either expand the simplex or contract the simplex. So, that will lead to more efficient search for the multivariable function. So, now let us see how you do that. So, this is we just discussed. Then when the optimum is approached, the last simplex straddles the optimum point or is very close to the optimum point. We may not get closer to the optimum point, and if we iterate further, the simplex may repeat itself. So, obviously, we need to change the size of the simplex to enforce convergence. We can consider midpoint of all the sides of the last simplex, and a new simplex composed of the midpoints may be constructed. The search is terminated when the simplex becomes small enough or the function values at all the vertices are very close to each other. So, this is what we have learnt in case of simplex search. Now, for improvement, would also want to adjust the step size. That means, when you reflect, I can go further along the direction through the centroid line if the new point is the best point when I compare all the points. That means, if the new point is best point, I wish to increase step size. If the new point is worse, then I wish to decrease the step size. So, this flexibility, if is introduced, it will lead to an improved search algorithm. So, Nelder and Maid in 1965 described a more efficient version of the simplex method that permitted the geometric figures to expand and contract continuously during the search. Nelder and Maid simplex search method will minimize the function of n variables using n plus 1 vertices of a flexible polyhedron. So, the main difference is, in case of simplex search or original regular sequential simplex search, we had always a regular simplex. So, we had a regular geometry. In case of Nelder made simplex search method, we make use of a flexible polyhedron. So, for minimizing n variable function, we will use n dimensional simplex consisting of n plus 1 vertices, but that will be a flexible polyhedron. So, these are the different operations that are possible in case of Nelder-Mead simplex search. Let us consider this first. This is the normal reflection that we have seen in case of simplex search that we have discussed in previous lecture. Consider the point x h as the highest point, the point where the function value is highest. That means, this is the worst point when I am minimizing the function. So, we need to reflect point x h through the centroid, and I get x nu as the new point. So, it has been regular reflection. Here I represent x h as the point where function value is highest, x l is the function value, is x l is the point where the function value is lowest. So, normally we will expect that the function value at x nu will improve. So, we can expect at least that at x nu, the newly projected or newly reflected point will have function value lower than the function value of the worst point x h. So, this is normal or regular reflection, and this is what we have seen in case of regular sequential simplex search that we have discussed in previous lecture. Now, consider now this case where after obtaining the regular reflection, you evaluate the objective function at x nu and you see that x nu is best among all. That means, the objective function value at x nu is even lower than the lowest function value. So, we have 3 points x h and this one and this 2. So, the new point that I get is best among all these points. So, in that case we will definitely would like to go further along the direction through which the x nu has been obtained. So, how far I will go will depend on the parameter gamma. We said gamma is greater than 1. So, I get a reflected and expanded point z. So, x h is replaced by z. So, the new simplex now will be consisting of this point and this point. So, this point is replaced and new simplex is obtained by these 3 points. So, I repeat, after regular reflection you obtain x nu, you evaluate the objective functions and you see that x nu is best among all. That means, the objective function value x nu is lowest, that means it has the function value lower even than the point x l where the function value is lowest previously. So, we extend it, that means we expand the simplex. How much we expand will depend on a parameter gamma. Why we expand? Because that is the direction in which the function value is decreasing well. So, we say that where the simplex is going in a nice direction, in a decent direction where the function value is decreasing well. So, after expansion you get the new point z and you replace x h by point x by point z. Next, let us consider that after regular reflection you see the objective function value at the reflected point is greater than the worst point or greater or equal to the worst point. So, what you would like to do? You would like to come back, you would like to contract. So, how much you will contract will depend on the parameter beta. Beta is less than 0. So, basically you would like to shrink the size of the simplex. So, note that you have contracted along the direction through which x nu was obtained and you have obtained the new point z by shrinking the simplex. So, this is known as contraction. So, the contraction is when you do a regular reflection and you see that the function value at the reflected point is greater than the worst point, in fact greater or equal to than the worst point, then you consider that the simplex will going in a wrong direction because the function value is increasing. So, maybe in the opposite direction the function value will decrease. So, you would like to contract. So, shrink the size of the simplex by contracting along this direction through the centroid of the simplex, and how much you contract will depend on the parameter beta, which is set then beta is less than 0. So, this is contraction which is actually shrinkage. Now, there is one more type of contract which can be obtained with beta greater than 0. So, after regular reflection you see that the function value at the new reflected point is less than the worst point, but greater than the second or next to worst point. So, you again would like to contract, but you do not like to shrink, because here the function value at the newly reflected point has improved when you compare the worst point in the previous or the old simplex, but at the same time the function value is higher than the next to worst point in the old simplex. So, we argue that let us go along the direction of newly reflected point, but let us not go that far. So, we contract, but we do not shrink. So, we contract with beta greater than 0. So, these are the 4 operations, and out of these 4 operations you see that these 3 operations are new, which is expansion with gamma greater than 1, contraction or shrinkage with beta less than 0, and contraction beta greater than 0. So, these operations introduced by Nelder and Mead leads to a more effective search for multivariable functions. So, now considering these operations, I now can write down the algorithm as follows. In case of step 1, you basically it is initialization. So, we set gamma as greater than 1 for expansion, set beta between 0 and 1, and we consider a stopping criterion. You generate an initial simplex, how will you generate initial simplex? We have discussed in our previous lecture. You have to find out delta 1 and delta 2, and given the scaling factor alpha, you can generate the initial simplex. Let x h be the worst point, that means if I am minimizing a function, x h has the highest function value, x l be the best point, that means for minimization of function xl has the lowest function value, and let us consider xg is the point which is next to worst point. So, second highest function value is at xg. So, you can calculate the centroid as shown. You just have to sum up all the points excluding the point where the function value is highest, that means exclude the worst point, sum up all the points divided by n. At step 3, now you reflect the worst point. So, compute the reflected point xr equal to 2xc minus xh. We now set the new point as the reflected point. So, set x new equal to xr. Evaluate the function values at xr. We already know the function values at all other vertices. If the function value at the newly reflected point is less than the function value at xl, that means the newly reflected point is the best among all, we perform expansion. So, when you perform expansion, the new point is obtained as 1 plus gamma into xc minus gamma into xh. So, this is expansion. Else if the function value at the reflected point is greater or equal to the function value at the worst point, we perform contraction. So, set x new equal to 1 minus beta into xc plus beta into xh. So, this will shrink the size of the simplex. Else if the function value at the reflected point is less than the function value of the worst point, but higher than the function value at next to worst point, we again perform contraction as x new equal to 1 plus beta xc minus beta xh. Note that these two steps are two different types of contraction. One in the previous slides was shown as beta less than 0, other was beta greater than 0. Here we are considering beta between 0 to 1. So, we are doing as 1 minus beta into xc plus beta xh, other one is being 1 plus beta into xc minus beta into xh. So, now we calculate again the function value at the new point and replace the worst point by the new point, which is obtained either as expanded point or contracted point. So, again now we have the function values at all the vertices. You now check for convergence. One way to check the convergence is the difference between this centroid and all other vertices are negligible, less than the value epsilon. In that case, we stop, otherwise we go to step 2. Now, let us consider an example. We consider a function known as Himmelblau function. Himmelblau function is x1 square plus x2 minus 11 whole square plus x1 plus x2 square minus 7 whole square. Let us find out the minimum of this function. Let us consider we have obtain 3 points x 1, x 2 and x 3. Of course, we know given any point x 1, I can find out those delta 1 and delta 2 and can obtain x 2 and x 3, but let us say I have been given x 1, x 2 and x 3 as say 0 0, 2 0 and let us say 1 1. So, the function values, let us calculate, let us the function value here is, so f of x 1 is 170, f of x 2, if I calculate it will be 74, and f of x 3, if I calculate it will be 106. So, the worst point is x 1, set gamma equal to 1 and let us say beta equal to 0.5. You also need to see set epsilon as a small value, let us say 10 to the power minus 3. So, what will you do now is you will reflect point 1 x 1. So, now x 1 is the worst point, the best point was x 2. So, the next worst point was x 3. Calculate the centroid. So, it will be x 2 plus x 3 by 2 and that you will obtain as 1.5 and 0.5. So, get the reflected point x r as 2 x c minus x h, which is nothing but x 1, and we will obtain this as 3 1. So, now the function value has to be obtained at x r. So, if I obtain the function value at x r 3 1, I get the function value as 10, which is best among all, because as of now XL was 74. So, I would like to expand this, because this is the best among all. So, how do I do that? So, to expand, I get x nu as 1 1.5 is the gamma, x h. If you do that, you will get 3.75 and 1.25. The function value here is 21.4. So, now these 3 points you consider, the old point has been replaced, the previous 2 points and these expanded new points will constitute the new simplex, and you can repeat the process. Now, I will show you how you can solve the same Himmelblau function using MATLAB's inbuilt function fmin search, which actually implements this Nelder-made simplex search method. So, to do that, you first write the function value, where you write down the expression for the Himmelblau function, and then call the solver fmin search as shown. Here x 0 is the initial starting point, and this instruction options equal to optimset, display, iter, tolfun, this instruction tells MATLAB that the MATLAB has to display the results at each iterations. Tolerance value has been set as 1 10 to the power minus 8. So, this is the last line represents the syntax which you have to follow to call fmin search, which is a built-in MATLAB function for solving a multivariable unconstrained function using Nelder-made simplex search technique. So, fmin search implements Nelder-made simplex search technique. So, to make use of MATLAB's inbuilt function, you first have to define the function. You can write it as a separate function file. Let us call this function as, let us say, Himmelblau fun. Okay. This is the name I have given, and then call it as follows: fmin search at the function value name Himmelblau fun, comma x 0 is the initial starting point, and options, where you ask the MATLAB to display the results iterations wise. It is optional. Now, if I do this, now if you run this code, you get this result. So, MATLAB uses the default values for those gamma, beta, etc. I have shown the first 10 iterations here. You see that function value starts with 170, same as we discussed when you hand computed it, and it goes on expanding it. And here I show the last few iterations where it contracts inside, which we call shrinkage. So, these are the steps. So, this is how we can solve the 2 variable function by making use of MATLAB's inbuilt function fmin search. With this, would like to stop here.